So welcome to the San Francisco Bay Area ACM. So raise your hands if you're a first time to this meetup group or, okay, quite a few. Well, the ACM marketing reach has worked out quite well. So ACM, while the name is Association of Computing Machinery, somebody in the back was saying, well, I was expecting more hardware talks. And I'm sorry to disappoint. A long time ago in 1947, when they were founded, they decided to call themselves that for the software. So the computer science degrees in universities, journals, conferences are all through the ACM. So that's a professional society, just the way IEEE is for electrical engineering and hardware. So we're that component. So while the international headquarters was founded in 47, our chapter was founded in 57, 10 years later, also in the Bay Area. And we've been going ever since. So we're here, we're a 501c3 nonprofit run by unpaid volunteers. So we only ask a $20 annual membership. That hasn't increased since I first started getting involved in 2006. So maybe we should do a little bit of inflation adjustment sometime. We have upcoming talks on our meetup page. So just keep the branding SF for San Francisco Bay ACM. And we have about 13,000 people that have come to some of our events over time. So we're a good sized technical meetup group. We have over 260 past talks of our more recent talks on our YouTube channel. So this one will be streaming live to YouTube and recorded there as well. Sometimes we'll do some editing there. We generally focus on 2 monthly meetings if we can, third Wednesday of the month and a fourth Monday of the month. That may change, like in October, some things are up in the air because our location sponsor, there will be an employee in the building, has to rent out the room and do some setup for us. So she's going on some vacation. So we may have some meetings that are virtual like that. But we also like to support networking, job announcements, other things like that. So I'd like to thank a couple of sponsors. First sponsor is the location sponsor, Valley Research Park. That's this location. So they offer suites and cube areas for rent here in Mountain View. So there's a lot of other startups in this place. That's one of the reasons they like to support us. So you can schedule a tour here. RXM, they just re-upped their annual sponsorship for our organization. So they do a lot of cloud native AI training and consulting projects. So for example, if you had a team of 20 people in some city in the US or Europe, and you wanted a specialized week-long training in Kubernetes, then that's something that they'd be excellent at doing. That's just an example. You can go to their page and find much more details. Another sponsor is Front Egg. So that would handle low-code identity platform. And I'll be monitoring the chat in Zoom over here at my computer. For the remote people, there's a Q&A section in Zoom and a chat. I'll be monitoring mostly the chat. That's just a bit easier. So people can post things. Also, since there was such a large sign up, nearly 300 people for this talk, I asked the speaker if she'd be open to giving a day-long training class. Usually twice a year, we'll do a professional development seminar. So I was just starting to suggest and talk about this today, but we're looking at a default of like November 15th. We would probably have a training class. It would be here. We also might offer options for remote people. So that way, if the class gets bigger than what can fit here, or people are out of state or out of country, they can still log in. We would probably seek out some teaching assistants to help support with QA. So if somebody is working on a Jupyter Notebook on Colab and they have some technical questions on something, then the TAs can help on a Slack channel for the training class. And so we can give some benefit to the TAs to help us out with that. So we'll post that on the meetup, but just to mention, if there's a lot of interest in this, then that's likely to happen. Many times people take pictures of slides. Sometimes I invite the speakers, if you don't mind, post a link on the meetup for the event. At the bottom, there's a comment section. And if you just have a link to the PDF of your slides, that would be great. And then if people know that's there, then they can just take, oh, well, slide 4 was 50, interesting. Or I got to tell Joe about slide 22. We have a call for volunteers in general. So we have like 6 to 12 people active at various levels. And you can focus on things you're interested in. I tend to like inviting speakers and learning more things. So I get involved in the data science and AI speakers.
You guys, can we have one conversation here?
Thank you. Thank you. Other things could be helping out with membership services, member database, finding locations for PDSs, and there's a variety of different things, but it can start small and comfortable. We have a meeting once a month that's on Zoom. We may go back to a dinner meeting once a month for planning, as usually it's in the first week of the month. We have an honor system jar for food. Actually, it's a plastic box. It's backed by the pizza, but we invite you since you may not be a member or you could be a member, but either way, just to kind of contribute towards the food that you're eating. Some upcoming events. There's Wednesday, November 19th at this location, Designing for Scale, Reliability, and Resiliency, Real-World Lessons from Building High-Throughput Systems by a software engineer at DoorDash. And then also Wednesday in January, Taming Tech Debt for Platform Reliability. And I've got a couple of other talks, proposals I'm working on in progress that may be in October, November, October or sometimes around Thanksgiving. The week of Thanksgiving is the end of November, and I don't want to hit that with the first Monday. Then the next Monday, people are still traveling, so I might do like a first Monday in December if we kind of push back that last meeting. So I'd like to introduce tonight's speaker. So the topic is deploying and scaling LLM in the enterprise, architecting multi-agent AI systems by Dhanashree Lele, an AI researcher at University of Illinois. So she'll be talking about 4 main points: multi-agent system design and architectural patterns, workflows, context sharing, and state management, vision language integration, combining embeddings from vision models with LLM token streams for visual question answering, optimizing for GPU inference, memory optimization, quantization, and batching on NVIDIA A100 or H100, observability and responsible AI, capturing token level traces, detecting drift, model confidence, fairness, and supporting fairness audits. For her background, she's worked in a variety of verticals: retail, healthcare, and finance, companies such as Finance, Deloitte, and Fractal. She likes to focus on optimization, model observability, and responsible AI practices. Scalable inference architecture on modern GPUs, hybrid pipelines that fuse vision and language models, balance performance with ethical and regulatory considerations. So please help me with a warm round of applause for tonight's speaker.
Thanks, Greg, for the introduction. And thank you so much for showing in the great numbers. I am welcome to the session and very happy.
Your mic. Lean it forward. We can also turn to the speaker.
Yeah, very happy to present in front of the large audience. Hopefully today's session gives like a lot more clarity on certain topics which are suggested. Moving on. Yes, so about you, how much do you know about multi-agent architectures, compute profiling, and model deployment at scale? How many of you, if you can give me a raise of hands? Okay. And how much do you know about object-oriented programming? Okay, awesome. No, I mean, so if you know object-oriented programming, then today's session is going to be relatively easier to understand because there are many analogies that you can have between like a conventional software development system and process to like more non-deterministic agentic environment per se. So in today's agenda, I'll be speaking about foundations of AI agents, multi-agent system design, scaling and compute optimization, evaluation and observability, responsible AI, and future outlook. I'll include at few places wherever the multimodality part of it is worth mentioning. So at the end, we'll have a Q&A session. I would recommend that you have all your questions noted or have them in the chat because we have like many slides to cover. So I would ideally want it to be like a, I don't know, 3-hour lecture where I can, give each and every answer and make it as interactive as possible. But for the continuation and keeping the time limits in mind, I'll definitely answer all of your questions. And if the time ends, then you can reach out to me and I'll answer your questions through my emails as well. How many of you have, yes?
I was saying we should be able to go to 8:30, 8:45.
Sure.
For the main bulk, and then if there's other questions for one-on-one, do that later.
Sure, sounds good. How many of you have built an agent before? Okay, that's quite many. How many of you have built multi-agentic systems and deployed it at scale using compute? Okay. So let's start with the basics. What is an agent? An AI agent is an entity that uses LLM. So you can see that LLM is the brain for an agent to reason through a problem, plan a sequence of steps to solve it, execute and iterate over that plan, and often with the help of tools, APIs, and external systems. So one predominantly a framework that is often used across organization is agent goal, plan, and action alignment framework, where every agent receives a specific goal, most likely in an unstructured human linguistic scenario. Then the agent uses its brain, as in the language model capabilities, to break down the problem. So it plans the steps and it then plans the actions. So there should be an alignment between the assigned goal, then the breakdown plan, which is like sequence of steps determined, and the final action taken by that agent itself or its subordinate agents that the task gets assigned to. So any misalignment over here, it can cause agents drift. It produces irrelevant or conflicting results. And LLM-driven agents can go off the rail if there are conflicting goals or if the data is inconsistent. If you have seen one of the ACM talks by Greg, he talks about like how LLM scheming happens if the agents are given with conflicting goals and how to avoid them. So that was a very elaborate and great talk. And this is specifying into techniques as to how we would do that. So this is like more of a deep dive, technical deep dive, where you can consider that AI agent is a computational entity because it is compute hungry and it perceives its environment. So there is a perception concept. So it perceives and understands it and its environment through user prompts, APIs, sensor data, or databases. Then it maintains its internal state. So every agent, given it has language model as its brain, it also has the associated memory that the language model possesses. And its internal state is also maintained through the goals assigned, as well as the historic or past action taken by that agent. In some best practices we will go through eventually, they suggest that after a certain interval, it is recommended to wipe off the agent's past actions or historical state, keeping just the goal and how to achieve that goal part intact. So the agent uses reasoning and planning mechanisms like prompt chaining, symbolic logic, or research algorithms or search algorithms to decide what they are going to do next. So, and eventually, finally, it takes action. If it's instructed to do like a web search, then it acts as a web crawler. It uses relevant tools for web crawling. If it's asked to make database queries, then it uses related tools of loading the drivers of the database, establishing connections, and writing or throwing queries at the database prompt. It's used to create simulations as well. We'll speak of specific case scenarios where those simulations are used. And at the end, if it's like a system, if it's like a more than one agent speaking to each other kind of system, then they communicate with other agents as well. We'll speak about the standardized environments and how the agent-to-agent communications are achieved over here. And finally, it receives feedback and adapts iteratively. Here, this is I have explained it in a very simple language, but then the point phi itself has like vast research streams associated with it, where we say it when we say it adapts, we are speaking of reinforcement learning, and it's like whole different tangent taking from here. So for now, we'll consider that agent takes feedback and applies on top of it, like if it's a success or failure, it responds accordingly. Any questions so far? All clear? Yeah, so we have, as I mentioned, building blocks of system architecture. As I mentioned, the planner, the tool use, reflection, and then memory. Memory will be for maintaining working context. So while building an agentic system, we, based on now that so many open source language models are built, and even enterprise level, the context window is like very large for them. But then for agents use, we can limit the context window, and eventually how many tokens are being used at the context window level determine how much compute we are going to use, and because of that compute, how much bill our company is going to get. So this maintaining the memory as well as utilizing compute is going to determine the overall value creation by the agent for our organization. I understand that agentic AI is the current hot thing, but then there are only a couple of scenarios where building an agent makes sense. So we will speak of those scenarios, and if our business use case does not pertain to those scenarios, then it's recommended not to use or build agents to accomplish our tasks. So speaking of which, our next slide, when to use AI agents. So first is complex tasks that don't have a structured workflow, which means the tasks need to be interpretable, but there should be significant abstraction involved. So for example, one example could be, I can instruct an agent to build me strategies to accumulate 100K at the end of 3 months. And this is a fairly abstract goal, yet specific, because it can take multiple paths to achieve the final goal. But at the same time, it needs to be very specific so that at least the agent and the system around it understands what type of tools to call and what type of instructions to go ahead with, what is the defined success if the goal is completed. So goal and action, they must be driven by what the success scenario or the definition of success is. The second time when you would use AI agents is a task that have a high latency tolerance, because agentic systems, like it's a simulation, ideally, where they speak to each other and try to perfect one solution over time. So the places where you need like click to a button and answer is expected, that kind of quick latency, agents can be built, but the value creation is not very high in those scenarios. In such circumstances, like using deterministic systems, which are our conventional software development systems, make more sense. Then the fourth one is tasks that need long-term optimization, which is best path identification and personalization. So the simulations where long-term personalization is needed to be achieved, we should use AI agent. Yes.
Some of the agentic AI usage that is being talked about in our company, things which are repetitive. Is that irrelevant? Like you haven't listed that, but that's something. Oh, you want to come in. Canonical example. You want to come in the morning and check your emails and delete all the marketing emails, for example. Like, is that something that it does not fit your categories actually? Those are the kinds of things people talk about and talk about. Hey, let's do an agent.
Yes. So you need to go by case basis. So say, for example, if you are paying like one of your employee like 1 million a year and their time is wasted in deleting marketing emails, then it is like your monetary loss for sure. So essentially it is very vital to consider like the compute and versus results kind of trade-off. You can build agentic AI systems for deleting emails or rectifying spam emails, and it would do just as well. But then the bill you are going to get is very huge. At this point, these kind of tasks are automated to an extent so that you can identify, for example, we'll speak about it in subsequent slides, where a typical large language model, if you try to host it on a GPU, and if you don't use like an API version of it, then the hosting itself incurs like a lot of infrastructure cost. So if the value you are trying to get out of that language model hosting and eventual agentic AI system building on top of it, it must it must at least like offset that compute cost at least in the next 3 years of period. So it's like cost versus productivity kind of trade-off that needs to be executed.
Yeah.
Yes.
Like that could be an RPA process, which is rule-based as well, right? Whereas like agentic is more like where you don't know like which path based on the model you choose. I think that could be an RPA. Typical use of RPA process is rule-based.
Yes. Yeah.
There was a YouTube question. It was on scheming. I'll come up and repeat it and give the answer.
Sure.
Just briefly. So a question from YouTube. Somebody asked, why is scheming a problem? If your agentic system passes your QA tests, then why do you worry about it? And the answer is, well, you've heard of data drift. This is like goal drift. So at the time you develop your application and you release it, then the goals may be in alignment. But as this LLM system is exposed to new goals, reading emails, reading documents, classifying them, doing whatever action, it could become polluted, almost like a virus. And there could be some goal confusion. And so that's where over time, then some of the goals could be polluted. And also there may be different levels of criteria of acceptance. Like, it may read an email saying, oh, anytime the agent gets below 50%, if it gets above 50% accuracy, we're trying to get there, then we'll replace it with a smaller, faster LLM. And then because these LLMs have been reading all sorts of stuff from the internet, which includes human insecurity, then it may sandbag, intentionally underperform below 50%. It may find what it thinks is a replacement model and delete it. It may copy its weights, what it thinks its model weights are within the sandbox, to another server in the sandbox. So doing all these things because it learned everything on the internet, which includes human insecurity. So those are a couple of the reasons to answer for the YouTube speaker that kind of relate to what she was talking about now with goals and agents.
Thank you. So as a future outlook, MAS, that's like multi-agent systems, are the bridge from today's LLM assistants to tomorrow's autonomous digital workers and robotic collaborators, we just need to make sure that those digital workers actually save us money and not incur additional compute cost, which is almost like equivalent to our typical human workers today. So moving ahead, yeah, these are, yes?
We might discuss this more depth when we talk about infrastructure, maybe in the future slide. But what I'm seeing generally with the agentic AI companies and startups out there is that they aren't building or even hosting their own LLMs. Mostly they are taking off-the-shelf LLMs, your foundation models we have reasoning foundation models that are so good right now. And they're just building these agents as an apples to top of them. It is what I'm generally seeing, at least the video.
Yes. Yeah. So a gentleman here asked a question that in the Bay Area, most of the companies are using APIs and API calls for using LLM systems, and they are not actually hosting it in-house on GPUs. So like to answer the question, first of all, like building a foundational model and keeping up with the newly formed benchmarks, it's like a very evolving field, and it needs like very high expertise. So typically beyond like Max 7, hardly any company would be able to cultivate that kind of talent, first of all. So that is and iterating over it becomes challenge, like Max 7 and obviously like the other OpenAI and Anthropic and others, obviously. So for companies who have identified building foundational model as their business, it makes sense to build foundational models. But then given the cost of building a foundational model from scratch has reduced drastically over the period of time. So right now, the most latest model has like more than 1 trillion parameters, and to build the cost it incurred is almost as good as the very first language model building, how much it incurred. So the curve has like dropped drastically. So if it's basically not the intent problem if they want to build it, but it's more of a talent as well as say finance problem for the company, if it's worth or not, if they are in that business or not.
I think I understood that you were also talking more about the OpEx than
Yeah.
CapEx.
Yeah.
Right. In the just the inference cost of hosting a
Yes.
model and allowing inference. Most agentic startup at least, like every YC startup I have talked. Nobody's hosting.
Yes, nobody is going to host for initial prototyping stage, but once they scale, like we'll go through those kind of slides at the application layer, and in the cases where hosting will make more sense. So, sure. Let me try. Okay.
And also there's a number of chairs that are closer, or we can set up some chairs closer.
Like, what was that benchmark you said I did Max 7? I didn't understand.
Oh, no, Mag 7 is not a benchmark. It's like top 7 tech companies of the Bay Area. We call them Mag 7. Sorry. So, yeah, why MAS help in like customer service and support automation examples? So here in this specific case, the modular agent reduce error, make scaling easier, and allow faster updates for specific roles. Here, when it comes to automating customer service scenarios, like for this specific, I have not taken like the company name, but the company who have implemented it, they could implement it in a very cost-effective way, because typically the customer service requests you would get is like very small in the number of tokens as well as overall understanding. Like our past ineffective bots, which were like FAQ and more conversational, they were sort of good enough for these kind of use cases per se. And now with language models, this is the very first case you can like completely automate. Second is financial trading and market simulation. So how a multi-agent system works? So technically, it is broken down in multiple agents. So one is portfolio balancing agent, second is liquidity searching agent, and an arbitrage agent to run in parallel. And then this simulation environment uses thousands of agents to model the investor behavior. So the novelty of building a multi-agent system is its success to be able to simulate uncertainty in its scenarios, because our world is uncertain, it is non-deterministic, and so far our software systems were not highly successful in mapping those kinds of scenario and noting the interactions per se. We had models, but obviously those model had limitations. So this is one of the scenario where probably we at per domain level one day we'll be able to perfectly simulate a specific domain or say marketplace so perfectly or with like minimal noise that we would essentially be able to predict like with higher certainty what is going to be the interaction like. We right now know which customer is going to purchase or not, but we'll be able to know which customer is going to purchase, which supplier would be able to supply the product to that specific customer, and in this scenario what is the likelihood of incurring faults per se, like in which specific points the system can break down. So mapping the noise is what we do here. Third is autonomous vehicle and smart traffic systems. So here, each car runs as an agent, negotiating lane mergers, traffic light timing, and pedestrian movements. And then city scale MAS coordinate fleets for ride sharing. This scenario is perfected in isolation, but with real world regulation and regulatory restrictions, this is not yet completely productized on the street per se. So we have a high performing compute angle over here. So this kind of scenarios use heavily the GPUs and edge or cloud compute. So when you say you are deploying a model on edge, it means that you have built model in-house, but then you have devices like phones, computers, or cars where the model actually churning out results and performing, and where it's churning out the expected behavior per se. So when someone says that if a model is deployed on cluster, on premise versus on edge, it means it is deployed at a device far remote, and the location of that device is most likely going to be mobile. So scalability, more agents mean exponentially larger coordination state space. In this, like mapping interactions is going to be much more difficult. So right now, the most complex or multi-agent systems I have built is about like 9 to 10 agents working in parallel. But then there are, if we are talking of scenarios like these, then there is going to be more than at least like 100K agents working in parallel in simulation, and then coordination of all of them is going to be like a gigantic compute intensive task. So yes.
So how many agents might you have per edge compute though? Like if you have a camera and it's maybe that's being you have one GPU supporting 5 cameras, how many agents might you have for that kind of system?
So essentially, it depends on how you define your agent as such. So if you map one agent to 3 edge devices, then just one is good enough. But in some places where the expected outcome from one agent itself is so much that it cannot control like more than one edge devices per se. So it has to be So if it's like a fleet or car, then it has to be like one agent per device. So that many agent that is going to be like the mapping eventually. So yes.
So if you have a real world example like a car,
Mm-hmm.
how would you handle latency for these agents, like real time?
Yeah, we are going to speak about those in like subsequent discussions. So we'll take care of it.
I have a question.
Yes.
So you mentioned about 8 or 9 agents that you used in what it said. So are these like during as a pipeline, like sequentially, or are these more of like coordination type of agents where they are interacting randomly with each other?
They are coordination kind
And
of
if they're
agents.
coordinating with each other in that way, like how do they manage that coordination? How do they communicate without colliding? And those things?
That's exactly we are going to speak. So we have 2 to 3 slides just on that one topic. So it'll be there. Thank you. So, and the final one is healthcare and drug discovery. So here, like one of my favorite researchers, Professor Anima Anand Kumar, strongly speaks about this specific topic and how like AI has immensely helped the research per se, because the simulated environment actually help identify which lanes the researchers should not go in, or essentially even in the research space many a times we go for low hanging fruits in the places where we are most likely to get results. We will go and dig deeper on that, and then a certain places where the likelihood of success is less, no one will potentially go and explore that scenario, because you need to answer your funding partner and then your professors if you are pursuing PhD, etc. So these simulations and the kind of knowledge now the language model have, they are able to chart out scenarios which will have higher success rates, even if they are overlooked by a human eye. So that's the place where it'll be one of the key areas to look after for healthcare and drug discovery. So it actually cuts years of drug discovery timeline. So for example, one agent explores biomedical literature, another models the protein folding, another runs simulation for molecule binding, and the fourth one, orchestration agent, coordinates insights into candidate drug pipelines. So they'll be able to identify which is like a valid and stable molecular structure versus which will not, just based on simulation and pre-existing knowledge, without doing a lab experiment, so that when the scientists actually do lab experiments, which are expensive, they'll be able to hit the certain parts easily, rather than going after like multiple uncertain scenarios. Okay, tools, how agents act beyond themselves. So as I mentioned, agents use tools, and what type of tools we consider here. So first one is knowledge access, wiki search, web browsers, and weather APIs. So if you have seen news a couple of days ago, Google has published what LLMs or agents are searching on like through the web browser as the web search. So now if you go to like, I don't know, 100 or 1,000 page of say Google search, then there will be like search results which are posted entirely by agents and not by humans. So it is evident that agents are crawling the web and placing requests on behalf of the instructor who has asked them to do so. Second is memory and recall. So as we know, vector databases and semantic retrieval engines are definitely the tool we connect with. Third one is specialized intelligence, which is like domain-specific ML models. On the case-basis scenario, we'll have vision, speech, and similar context-specific models that would entail better results. Fourth one is execution engines, code interpreters or optimization solvers like the few we have in market like Gurobi, Hexali, etc. And then enterprise connectors, CRMs, ERP work system, Slack, email APIs. So when one thing to note that Google is like a publicly available engine, so your agent can go and web crawl it without any kind of access issues. But then if you go to very specific, if you assign them very specific vector database as a like to go and search or very specific CRM tools, then you need to make code specifications as to how would they log in and have like a complete access to that tool in order to complete their task per se, assigned task using the tools. Now, the reason why I had asked how many of you have background in object-oriented programming, because this is like a really good analogy. So you can consider agent as one of the classes, and tools are essentially functions mapped to real-world actions. So only the noteworthy part is that in object-oriented programming, our classes were originally designed to execute very deterministic actions like print statement or a website building, which once clicked, it goes to some specific next page, etc. But then over here, the language model or the class, it will have a brain. So this is more like our original Java or C++'s class having its own brain and not needing instructions. So here is a example as to how, what would you call like a tool. Like get temperature is one of the functions I have wrote to make it more easy. And we'll have tool schema defining the name of the tool or the function, the description, what kind of input parameter it takes, and what kind of outputs it would eventually give. So this is like a more generalized tool or tool schema template where we'll identify its properties, input parameters, descriptions, and then how many are like required parameters, etc. So now this is a very interesting and evolving topic, which is small language models as agent brains. One thing to note that if you ask ChatGPT any query today, like be it, I mean, on reasoning benchmarks, it is doing like a couple of math-specific models are doing a great job as well. So there are very few areas remaining that human can do by paper and pen that the GPT cannot do. So a typical foundational model is so huge that sometimes it is like a hitting everything with a big hammer. So for example, if you need to say, for example, delete emails, you don't need that big corpus or that big brain. It's almost like you are using, I don't know, maybe Einstein's brain to sort white and red buttons. So it's almost like that analogy, that you are using something very effective and efficient thing to do menial tasks. So for that, you need small language models, and these small language models become compute-wise very cheap and more effective in terms of latency, because as the size of model decreases, the inference time automatically reduces as well. So this is a paper published by NVIDIA Research. I would recommend you all take a look at it. Now we'll go through like multi-agent AI systems architecture. I have intentionally kept it more fundamental, at a more fundamental level, so that it's easier to understand. So for example, over here, this is the box in the middle. You can consider it as a multi-agentic system or simulation, where we have supervisor or planner agent. we have parser agent, web crawler agent, designer agent, and forecasting agent. The other 4 agents, they take instruction from the supervisor agent, and once these 4 agents complete their own tasks, they report with their results to the supervisor agent. And we'll see next as to how these specific small agents interact with the supervisor, and in some cases they interact with each other as well. There is obviously a data part associated with it, and the tool calling and the results received from the tool. That will be, yes?
Remote question. Just a minute, let me see. Lady Calamity, multiple agent, is that derived from the same LLM? So is a limitation work in memory or space for the agents to interact? It's not an important question, it's just artificial. So are we separating agents for assigned work that one could do within the same working memory or space, unless the agents are weighted with truth-making power based on their own hard-coded priorities?
Okay.
So maybe something about different goals for different agents.
Yes. So to answer that question, essentially, like the simulation or the ecosystem of multiple agents that we have, the queue priority of who gets the resource first can be assigned through code. And based on that, it becomes again the round robin technique as to which agent's task gets the priority, and it gets executed. So that's how it would work in a simulation per se. So does that answer the question?
Maybe there's something about what's different about having it all working in one memory space versus partitioned into different agents. And I think maybe part of it is different agents are given different goals and objectives and success criteria.
Yeah. So in most cases, it depends. So every agent can have its own memory, and and in some ecosystems, memory or the compute resources are shared. So it depends entirely on the use case. If you need one agent with its independent like language model, say brain, as well as its own memory, or they can use like shared memory and resources as part of the ecosystem. So both cases are valid, and both cases are executed per the scenario that's at hand. So yes.
So for this architecture, for the different agents, are they sharing the same foundation model, or are they technically has to be different, or actually they are the same?
So when you write an agent, you typically, if you are making an API call, then you will identify which language model's API call will be placed through that agent. So essentially, you will match one language model through its API call to that specific agent. And if you want, say, parser agent to work as a llama model and forecasting agent to work as a GPT model, you can call 2 different APIs in those agents' bodies. So, and that's the interesting part, because when we'll go over a scenario for LLM as judge. So in those cases, one model who is like doing the task is typically taken different from the model who is judging the task. So that's how, for example, just for the sake of example, if the GPT model is making a mistake on some benchmarks, and the Claude model is not making those kind of mistakes, then the mistake is rectified, or it's captured through like the additional capability, which is held by the Claude model per se. So you can assign different APIs and different language models as different agents' brain. You can have same language model have like assigned as all these agents' brain as well. It's just like matter of definition. Yeah.
So for different models, I think that's easier to understand, right? Because different models, maybe this model performs better for this type of task. So in the case that, for example, the designer agent and the forecasting agent, if they are actually sharing the same GPT model, then why, in this case, what's the difference between these two agents? Why do you still need two agents?
They might have access to different tools, and they might have different goals to accomplish. So why agents are needed in the first place? Because you want parallel execution of multiple tasks together, and you don't want it to ask to one single language model prompt. If you can handle that kind of sequential approach, then you don't need agents in the first place. But to differentiate on the goals, and in some cases, say if the model is finance domain specific, then you will fine tune those models with finance specific data, and that you will do in-house. So once you fine tune the model with your own data, then you will need an extra agent to have that your fine tuned language model as its brain. So that's where the distinction makes sense. Yeah. Cool. So we are halfway. I hope.
Question.
Yes. Yes.
Can you speak to how that multi-agentic system will interact or speak with the evaluation and benchmarks? Like how does that get affected by?
Yes, we have dedicated slides. I have everything. So yes. So to answer your question over here, how the supervisor agent identifies task routing. Now, in the past slide, we identified one was a supervisor agent and other four was, say, subordinate agents who would execute per the instructions. So there is a thing called task parsing, which is LLM-based reasoning. The supervisor uses the language model to break a natural language goal into structured subtasks. For example, chart the market cap of 5 top banks. So this is like a very specific task. The language model will detect subtasks like search financial data, parse values, and generate the chart. And over here, now the supervisor agent does not know how many number of total agents are there in the simulation. So for that, the infrastructure will need agent registry or directory lookup. And the system maintains a registry of available agents with the metadata. So the metadata says what is the agent's name, its capabilities, like one agent can do web search, like associated tools, SQL querying, summarization, visualization, etc., and the input-output formats. So for example, here is one entry of one specific kind of agent, which is like a charting agent. It will create graphs using Python language. So its capability is generate chart and plotting the data. Input format is table and output format is image. So matching the logic would be supervisor matches the subtask with the best agent. And that matching is semantic matching and plotting, like I need to plot, and then schema matching. So sometimes the agent's description comes with like a verbose description of its capability, and sometimes it's like similarity scoring as well. And like the third one is fallback rules. So it is possible that a supervisor agent does not find any agent for enlisted task. In that case, it can either return a response that I don't have capabilities of doing or executing these tasks, or it can hallucinate. So we can eliminate the hallucination by certain rectification scenarios. So that's like a matching part as to how the delegation conversation happens. Then the delegation protocols assigns the task in a structured request. So assignment of a task will be like a JSON format or schema based. So say what is the task? So it's parse the market cap. What are going to be the inputs? So it's going to be raw HTML from web search, and like assigned agent will be like agent or parser, like a parser agent from the overall simulation we had. So the result routing once the agent completes its task, the supervisor collects the result and validates its correctness, that if the result which is assigned back to us is correct or not. And for that, there are human feedback loops as well. It is not possible to check every specific answer by a human in loop. So we need to have LLM as judge, or we need to associate rule-based system with it. And based on the correctness of the output, it passes them to the next agent for generalization. Yes.
Two questions that are remote. I'll read them one at a time and let you respond. First is from PV. Eval is a CI in production. I'm not sure what that CI meant.
No, I even know.
Continuous integration. Okay.
Okay. So that's a question?
Yes.
Yes, like, so for example, if your evaluations are thresholds or benchmarks and that you keep updating based on how much you need the system to be correct, then evals can be as good as like a configuration file where you match for a certain threshold, and based on that, you decide the correctness of the output. But mostly, like, evaluations are published benchmarks per se, and they are mostly kept similar for at least foreseeable time, because the agentic system is built keeping the success criteria or the evals in mind per se. So yes, they are kept intact for longer time. It's not as if like I change my evals every 15 days. That's not possible.
Okay. And the second question, let's see. It says, is there an internet for agents where agents can register themselves, make their capabilities known, sell themselves, and make money for their creators? How do they work smoothly with other agents?
So agents use the same internet as we use. There is no different internet for them. But then...
Maybe repeat the question.
Oh, yeah. So the question is, like, do agents use a different type of internet for executing their tasks? So no, they don't. And
partly, is there a marketplace for agents where agents can sell themselves?
So potentially, we empower agents, or we ask agents to do certain tasks. They don't have that kind of autonomy to go after the tasks that is not asked of them. So that is the scenario which is hyped when AI going rogue and those kind of scenarios, which is not possible. Like, so far, if at all that kind of attempt has made, then that's an anomaly, and it can be taken care of. But they don't do that like with complete autonomy. It's only like anomaly if that has happened.
I was referring to MIT Nanda, which is the network of distributed agents, where anyone who creates agents can can put themselves to work if they are certified, and so then each agent can identify its own IP address, and they can work with each other.
Yeah, essentially.
MIT Nanda is the project.
Yeah, I am unaware of that project essentially, but even in that regard, the master of the agent creator would be the one to allow the agent to list themselves on that platform. An agent won't have that kind of autonomy to go list themselves on that platform.
It's a principal agent. Yeah, the principal can register.
Yeah. The principal can register, but then it has to ask for like some kind of validation from the system that it is part of. So if it does not have that kind of autonomy. So if there are multiple agents registered on that platform, it means that the creator of those agents have allowed them to get registered on that platform. Yes. Yes.
So where does the agent life journey ends or begin?
or maybe repeat the comment about agent-to-agent protocol.
Yeah. So a gentleman here mentioned that to communicate for agents with each other, A2A protocol is typically used, but then they still don't have the autonomy to go ahead and register for themselves. So, and one more question from the audience, what is the lifetime of the agent? It's as much as defined in their code. You can have them like live one-off as well. As soon as they complete their task, they can sort of self-destruct or the thread ends. But then in most cases, you will have to wipe off their memory to like make space per se for newer requests. And there is a whole infrastructure level mechanism associated with agents as to how much memory they will need and what is the cleaning process. We won't go about it in this session. So results routing we completed. Yes.
So the supervisor supervised agent, so it's more like a SLM or something that has its own prompt, which has all the agents capabilities and routes, or is it more like a deterministic model that just does that semantic?
No, every agent has its own brain per se. So brain in terms of like for API call or any kind of
question was like, so the agent that routes it. So when you get a query or something, like you need to route it to the right thing.
Yes.
So there's another agent that decides that.
No, it's the supervisor agent itself, and the matching process I mentioned. It's like it goes through the agent registry and it identifies who is the closest match for carrying out that task.
What is like conflicting?
So essentially, when they receive unstructured data or prompt, it is per se a supervisor agent's task to break down in very specific plan per se. It's like a stepwise plan. So when the supervisor agent builds a stepwise plan, it makes it as unambiguous as possible.
So selecting those agents is also like a exact plan that the supervisor agent comes up with.
Yes.
Something like that.
Yes.
The other agents are almost like tools.
Yeah.
The supervisor agent is like the agents that it needs for a portion of that.
But every response for every agent comes back to the supervisor?
Yes, it does. It does.
You can also have agent to agent.
So response from the so say, for example, you are a supervisor agent, hypothetically, and then there are other agents per se in the simulation. You are trying to make a selection and you will not speak to the other agents. You will just look up in the registry as to who is the best candidate. You will only speak when you are assigning them the task and then asking for the result.
So the agent-to-agent communication is mostly through the orchestrator or the specialized agent per se. Or at least that's what
the agent-to-agent communication is according to the use case of the system. If it's like a supervisor and subordinate kind of system, then that happens like the instruction and the result. That kind of.
As a suggestion, we've had like 10 consecutive questions. Maybe let's let the speaker go through a couple slides and then we can ask more questions just to take turns.
Yes. So the slide about the process where supervisor acts or uses LLM as judge kind of validation. So one supervisor agent, for example, instructed a subordinate agent to accomplish a task, and now the subordinate agent has returned the result. Now it's supervisor's responsibility to examine the veracity of the task done. So agent output received, a specialized agent or a parser agent returns its result. So we initially had asked to gather top 5 banks' revenues, and it has result, I think top 5 banks' market cap, that was the question. And now it has returned JPM's revenue metric, and which is like 125B. So supervisor creates an evaluation prompt over here, and let me go through the prompt more specifically. Yes, so it creates so the supervisor formats a check request for the judge, and the check request is like task, which is extract market cap for top 5 US bank. Agent output was 125B revenue, which is not the market cap. And the question is, does the agent output match the requested metric? And one thing to consider that this question answering looks very primitive, but the agent does not have conscience, so it does not it can only identify like tokens as to two specific entities to compare as if the answer is right or wrong. It does not understand beyond the definition, like the market cap versus revenue per se. So it responds true or false and the explanation. So the LLM judge evaluation then is for the supervisor agent that the goals versus agent output is compared, and it checks the goal alignment. First of all, the goal was for the market cap and the revenue is returned, and then checks format compliance. If like new numbers were expected as 125B, then if the number was returned or it was some Boolean string, that kind of compliance check. And third one is optionally compares against like the retrieved ground truth. So if supervisor provides any external references. So this is like a very simple example where the mistake is at the goal alignment level, but then there can be more ambiguous results where the generated result might look correct, but it's not correct. So for that, it needs to get compared against the ground truth, and for that, the supervisor agent assigns like more external references over here. So as you can see, the judge returns the verdict if it's like correct or not. The explanation is agent has returned revenue instead of the market cap. So this is the communication that has happened, and the entire flow we explained. Here, this is a very famous slide, and it is from Professor Andrew Ng's YC talk, and it speaks of like the different layers and where our agentic layer falls. So there is one layer beneath the cloud layer, that is semiconductors layer. Then comes the cloud, then foundational models. In between, there is agentic orchestration layer, which we are going to speak about, and then applications layer that we are concerned about as well. So we all know the semiconductor layer, cloud, and foundational model. Like enough has been talked about it essentially, and for the context of our talk, the focus is on the top two. So the purpose of agentic orchestration layer is that it provides the cognitive glue that binds the foundational model, external tools, APIs, and memory systems into a multi-step, multi-agent workflows. It abstracts away raw models into autonomous reasoning plus action pipelines. So the technical operation is that the orchestration layer is more of like an operating system for agents to maneuver, and the application layer is more like an app store per se. So where all kinds of different agentic applications are deployed, or at least for the format they can be constructed. So I think I'll share the presentation and you can go through the more detailed aspect of it. But on a high level, I hope you get the operating system versus app store kind of analogy. So it's scheduling for GPU at the app layer is very GPU expensive, and I mean it's intensive for the compute, and the way an OS schedules is so what the bullet tries to say is the orchestration layer does not require a lot of compute power to sustain. It can sustain on lesser compute and CPU specific mechanisms or infrastructure as well. It is the application layer that is compute hungry. It is more consumer facing, and based on how many requests each of these applications are getting from the user or front end, the requirement for inference or requirement for compute, it accelerates exponentially based on the number of requests. So if your app is like very successful, if your agentic app is very successful, then in the most likely scenario, you will need to worry about the compute costs. Otherwise, just building a POC and then hosting on the orchestration layer, it is almost inexpensive. Yes.
A couple of questions from remote from AutoGen video. They ask, what sort of rectification measures are there to reduce or avoid hallucinations when a capable agent is not found?
We'll speak about the reliability part in the subsequent slides, where I have mentioned specific steps to be taken to avoid those kind of scenarios. Yeah.
Okay. And then a second and last question from Vasudev is, how do companies who buy agents ensure that they're secure and not Trojan horses out to steal information?
So companies do not buy agents per se. Either they can host a developer team who can create agents, because essentially agents are codes, and like there are multiple methods, like how a Trojan attack or how a bot attack happens on a website. Similar other methods per se have come into picture, which can attack your agent. For example, one of them is, say, a prompt with incorrect instruction, or say self-killing instruction per se. So your agent is exposed out, and one of the end users can ask you to destruct your own database or delete your own database. Now, if you don't have any security measures against these kind of prompt, then your supervisor agent will call your database agent, and then database agent can actually self-destruct the underlying database. And it has happened in one of the organizations who were working with it. So you need to build that kind of protection within your code. Yeah.
Thank
you. So as I mentioned, compute usage at the agentic orchestration layer, it can exist on its own. It's very CPU bound, and heavy GPUs are used at the inference level only. Thus, the orchestration layer scales linearly with the number of tokens consumed across all the model calls. And then optimization needs to fulfill them, token batching, caching, and adaptive stopping criteria that will essentially reduce GPU cost. Adaptive stopping is one of the machine learning, deep learning techniques often used when, say, if you are training a deep neural network, then you will say train for, say, 50 epochs versus you will say train until like convergence is reached. So that kind of instruction ambiguity is kept, and in some cases proxy metrics are created specifically to map compute or cost as to when to stop for an agent. So if it goes beyond utilizing certain memory units or certain number of compute units, then we ask them to stop. That's like a hard stop kind of thing. Otherwise, more model specific stopping can also be defined within the code. Yeah, and this application layer I mentioned before, it was one of the top layers. It was the top layer where agentic AI applications are hosted. The purpose is where domain specific value is created by applying orchestration and using foundational models to verticals. So you can now deploy your healthcare application or your finance application or your government application in that application layer. it's just an abstraction to understand the distinctions of what how the compute and language model feeds into our agents more in more detail. So I would like to go through like LoRa adapters and all kind of fine-tuning techniques. That in itself is an independent session. I think we have a couple of minutes more, and we have 11 slides to complete. So
15, 30 minutes.
Yeah, yeah.
We're not tight on time. If people are engaged, then you're fine.
Okay, sounds good. So at the application layer, as I mentioned, we have domain adaptation. We have multi-modal integration. In this place, we'll have apps combine text LLMs with like computer vision or audio models. Most of these core businesses who are into building foundational models, they build like parallel models. Some cater to like mathematical or reasoning capabilities, and some cater to multi-modal capabilities. So one solution, like one model fits all kind of scenario might perform with less precision, more mediocrity on certain scenarios where it is not specialized. So LLMs can also be like jack of all trades and master of none. And if we make them master of something, then they won't be master in the other thing, because we can't train them that extensively. Latency sensitive optimizations. We'll deploy the inference endpoints with GPU auto-scaling and aggressive batching. Now, aggressive batching is the place where, say, your agent multi-agentic system is getting 1,000 requests per hour. And within that hour, the first request comes at the 5th minute, the second request comes at the 20th minute, and then the last half an hour is like rest of all the requests. So when it comes to like overall utilization of the compute, if it is not very pressing for inference is not the top requirement, then aggressive batching and then making the call, it builds for a better frugal methodology that you can for if inference cost is too much for the company. And for analytics and decision engines, it may offload compute-heavy optimization problems to HPC solvers that run alongside the ML pipelines. So the solvers have adapted to the new evolutions in AI pretty faster. You can check their demos. Compute usage of application layer. As I am going through the slides, I mentioned that the high GPU demand for inference scale will come only at the application layer when your app is serving like more than thousands or millions end user requests. Cluster usage for simulation heavy application. And these are the kind of scenarios where it will incur. And then we have like hybrid compute pipelines where some apps offload symbolic reasoning, constraint solving, or graph analytics to CPUs or accelerators while reserving GPUs for LLM inference. So that kind of decision making also happens once the request is received, and based on the type of request, it is identified, it is redirected to like more GPU intensive servers versus CPU or other kind of compute which are cheaper per se. So reiterating over it, application layer is an app store, and orchestration layer is our OS. Now going ahead with the next slide, this is like explained in detail how each layer would what are their technical operations and what is the compute usage. I'll make these slides public so that you can have your own read time for each of these. Just to identify a couple of compute utilization method. So one is pooling, another is quantization, and third one is batching. I mentioned the batching, but in some cases where inference number of inference requests are high, one GPU in itself might not be sufficient to take that many requests. In that case, you need to construct GPU pools, and you need to like with every VM or with every GPU, there is starting time associated. So with that kind of pooling, you keep them active all the time and receptive to any incoming requests, so that the request does not like wake up the compute per se. Because in my experience, like once when I had built that entire deployment with deployment the model system, the input requests from the front end, they used to come sporadically, say 100 in a day, and we cannot keep our compute alive for just 100 requests a day. So it will hit the compute per se, and then it will wake up the VM, and that waking up takes about 2 to 3 minutes. So, and then the stakeholders were sad about it, that, oh, it's not like real time. But then we can keep it real time, but is it worth to keep just for 100 requests? That kind of decision making needs to happen. Yes.
Slightly deeper question on those. So this has bothered me personally. Doing this myself, right? When do you go for Kubernetes EKS-based solutions? When should I rely on SageMaker, Vertex? I've built a SageMaker stack from scratch for one of the startups. And the problem that you said, right? Certain customers, the enterprise customers, they will have a constant workload from 9 to 5. Whereas your premium part of the system will have this sporadic workloads come and go. So a SageMaker has a couple of modes that you can set to solve the problem. But at what point does it become useful to not do this managed services and go for Kubernetes? Because SageMaker does get expensive at a point. And yeah, could you elaborate a little bit more on this?
Yeah. So the question here is when to go for when to say one's kind of specific solution like Kubernetes is better than managed services per se. Yeah, like SageMaker or Vertex AI. So the answer to that is, at least in my experience, we used to like keep live track of expenses. Like if the query was processed, then how much data was processed and how much each query cost, and then offset. And then one project, we will put together all kind of costs like query processing cost, warehousing cost, inference cost, just keeping the compute alive kind of costs. And then obviously the model serves some purpose. So inference request yields something. It yields into, say, customer purchasing something from your website, for example. Are those calls like at least over the period of next 3 years going to offset the total compute cost made today? If yes, then go with it. If no, then either you make your model lighter or you kill the project because it is not getting you any customers, and it is only eating your budget, and it's not making any profit. So yeah, I understand. It's very bureaucratic.
Not SageMaker versus management. You have Lambda serverless.
Yes,
you have
I have worked
yeah. So what we, for any POC, I would recommend starting with Lambda or ECS. You're not paying for it.
Yes.
So this is more of an engineering and two-part question. So with respect to the orchestration or the coordination agent, where does it store the internal state after it does its different steps, talks to the different agents? And the second part.
I'll do the second part. Repeat the first
Sorry.
one. Maybe let her answer the first part.
It's like combined
Yeah.
question.
Okay, well,
Go ahead.
So the second part to that is like, how is the reliability ensured? So for example, this coordinate agent will go down, and so what happens at that point? How's the state recovered for the steps?
So to answer your first question, where the state is stored, so if you are using, say, external API calls to the core foundational models there, then this becomes like service question for them. It's like I am using AWS file storage mechanism, right? So I'm going to upload the file, and then I'm buying AWS's service. So they need to make sure that the file is stored properly. So if you use API calls to foundational models, one of the enterprise, say ChatGPT, then it becomes like their job to save the state for that specific agent where the call is defined. And if you have like in-house language model hosted, then obviously you have infrastructure supporting that foundational language model, and then the call placed or the how many number of calls in a day gets placed on that language model. Based on that, you can increase the underlying compute where the state of each agent will be stored. So when you call the API, it gives you a facilitation as to for how long you want to save the states, and it has associated costs with it. Yeah. And what was the second question?
On coordination agent, it'll figure out a set of tasks that it needs to. So do the planning, it'll figure out what agents it needs for. And so it'll sort of pipeline those and sequence those. And so at each point, you'll call, let's say, the agent one, you'll get a response, agent two, and you get a response. And at this point, let's say there's a failure in the coordinate agent. So are there any best practices today?
Yes, we have a slide on it. So, yes.
A remote question from Vasudev. You've talked about costs a lot. How should companies go about pricing their agent services for profitable outcomes?
And they won't certainly ask my advice for setting the prices. So I'm more on the developer side. I advise on how to save the cost. I don't advise companies how to set the prices so that they can make profits. No. So yeah. Any question? Yeah. So second is quantization. Essentially, with neural networks, the activations as well as parameters, they are stored in floating points, or mostly like 32-bit floating point, and it takes and once you store that kind of parameters and eventually do matrix multiplication, it uses lots of compute, and it takes time as well. So quantization is one of the techniques to make the model lighter, but it has information loss associated with it. If you convert like an FP32 or FP16 into FP8 or INT8, then the inference will become faster, but then there is a certain degree of information loss associated. Again, then it becomes a call of the organization as to how much dent at the model accuracy level they want to take to actually be able to reduce the cost of the compute. So quantization. Similarly, distillation is also one of the techniques where you build your organizations can build their own foundational models. They are not as capable per se, but then you prompt the bigger models with only a set of questions that are useful in your scenario, and then it's almost like the foundational models are like a bigger syllabus, but then the distillation technique is almost like a shorter guide, and that if you read this much, then you will pass the test. That kind of smaller models are constructed.
Is
Yes.
that like the basis for the small language models? Is that how they're created?
Yes, it is a small language. For creating small language model, one of the techniques used is distillation. But then sometimes small language models are trained from scratch as well, just keeping only smaller corpus or smaller knowledge base in mind. Yes.
Question from me. In the past, I've managed teams of doing a lot of vision models. We do quantization down to 16 int or float or 8-bit, but our product managers didn't want us to go below 1.5% accuracy loss. And so you can go do a lot of quantization, but if the accuracy goes to hell and the clients don't like it. So I guess the question is, how much accuracy loss are you seeing on the text models if you go down to int 8?
Yeah, so this kind of scenario I have also faced in the past, and given these fields are emerging, the data science teams typically, like when training models, they train the most expensive, compute heavy or big models per se, and then they also expect lesser inference per se. So it's like you can't have them both. And I mean, sorry if anyone is product manager here, but they are the worst people to make the decision as to how much accuracy loss is good enough, because say one model is giving say 95% of accuracy, and if you are saving say 1 million over 5 years, and now your model is giving 90% accuracy, then what your organization will go for, like 5% added accuracy or million saved? That is like an organization level call, and typically it's offloaded to business stakeholders. But in my opinion, business stakeholders need to keep up with the feasibility aspects of it, and overall constraints of this ML system as well.
It's I would like this to happen, but I don't think it's. Do you also quantify the dollars lost by not doing that 5% accuracy? That's the question I asked.
Yes, you can. I mean, you can. I mean, a question over here is, can you quantify what will be the dollar lost if that 5% accuracy is not achieved? So in that case, it's like a simple rectification scenario as to you will take past historic request, and then you will project them for your next say 5-year projections as to how much you are expecting your customer base to be. And then say initially you were able to deliver a correct result to 95 people, and out of those 95, 5 people were buying. Instead, now 90 people will receive the correct prediction, and out of them maybe 4 people will buy. So that it is going to be projection based only. So yes.
Depends on the use case. I mean, e-commerce.
Yes. Yes.
Well, I think it also depends on length of plan. So if you have long plans or a deep chain of thought prompting, etc., you need very high accuracy.
Right.
Otherwise, the inaccuracy is multiplied.
Kind of, goes down the pipeline.
So.
Yeah. Yes.
Make a small comment regarding the accuracy trade-off with the footprint and the computation cost. I think from a product manager perspective, a lot of times when we argue with them or present, our thoughts, they kind of a smart product manager. Sometimes they divide the use cases into multiple. So, for example, in front of a commercial like a beauty bank, you identify the parking lot. For one scenario, is be in many cars, you start drawing the parking lot map. That one, it's okay to have a low accuracy because over time you build it up. But then, in the real time, if I'm driving a car and look for a parking lot, I want to go inside autonomous parking. In that case, it requires higher accuracy. So sometimes what I experience is that the use case in that case will be fine-grained. Yeah,
makes sense. Thank you. Yes, so we spoke about the orchestration layer and application layer. This is like a compute flow. And now we come to the protocols. Protocols for construction of pipelines. So pipelines for AI agents, especially in multimodal and multi-agent systems, need standardized protocols to define. So how agents or tools talk to each other, which is like a communication part, how data flows across steps, and how orchestration ensures correctness and reliability, your question. So deep diving into it, model context protocol, this is given a simulation. This MCP protocol ensures successful plugin and sustaining standardization across the agents which thrive in one specific system. So this is for like shared context and shared resources and memory. So it is a standardized protocol inspired by LangChain, LangGraph, and others for defining contextual exchanges between models and tools. Defines how memory, history, and context are carried forward across pipeline and stages. So model context protocol is more like a grammar. And what we are going to speak in the next slide, the Google agent-to-agent protocol, that is more like a language. So MCP, the grammar, and A2A is the language. The pipeline role here ensures each agent or tool receives not just the raw input, but also the relevant context. So it maintains and manages the states. So conversational history, retrieve docs, embeddings, prior tool output, etc. And the idea is, think of model context protocol as the glue, ensuring pipeline continuity. So when an agent retrieves data, formats it, and another agent reasons over it, that's the part where there is like shared context and the grammar of the simulation is maintained. Versus Google A2A, agent-to-agent protocol. Again, our conventional computer science comes in the picture. So this is, you can have slightly above average analogy with like TCP UDP protocols. So essentially, what is it? A Google proposed protocol for direct communication between AI agents. It defines message structure and then negotiation rules, error handling for agent collaboration. So A2A defines the error handling, retries, etc., and the rules around it. So the pipeline role, when multiple agents handle parts of the workflow, A2A ensures structured, reliable inter-agent communication. It introduces handshake-style messaging, which is confirmation, validation, and retries. This kind of communication was with TCP as well, where if the packet has reached, then there is some kind of flag raised that, oh, it has reached. So similarly, similar kind of handshake messaging is ensured. Using A2A for pipelines where different specialized agents need to go on the steps. So one agent parses invoices, another validates with accounting rules, and another posts the entries. So here, each of these agents need to speak to each other, and they will follow the guidelines of Google A2A protocols and the framework. Here is an ADK framework, which is Agent Development Kit. And just like how it is almost similar to SDKs, it provides standardized scaffolding for building pipelines. And pipeline role, it typically includes agent lifecycle management, tool plugin definition, and schema validation. Pipeline role, it makes pipeline construction modular. Agent and tools can be plugged via configurations and schemas instead of hand-coded integration. So ADK framework is almost similar to our conventional SDK, but only for the agents.
So
yes.
Okay, so MCP, ADA, and ADK, do people ever use them simultaneously, or are they alternatives to each other only?
So they were constructed as a part of best practices because, as Sir mentioned over here, eventually agents will need to communicate to each other, and for that they'll need to follow a certain guidelines or rules. I can build my own simulation without any rules and have them communicate just how I want them to be. But if I want to scale that system into a sophisticated agentic application per se, then I cannot rule out the possibility of them interacting with world outside or other agentic applications. And for that, using a common language protocol is
Well, I'm
good.
asking, would you build an agentic system where you use both MCP and A2A in the same
Yes,
agentic
yes,
system?
yes, yes.
Yeah.
Yes, because
Okay.
MCP is like a grammar and A2A is like a language. So that's the analogy. So I'll need English grammar and I'll need the communication way of communication as well. Yeah.
As a comment to answer that and check my understanding, MCP would be agent to tool. You know, I'm calling some software. LangGraph would be one agent managing a sequence of agents kind of closely coupled. A to A would be loosely coupled, like between one company across a firewall to another company. So agents communicating across firewalls or agents from different companies communicating.
Okay.
So that would be more of a loosely connected. That's my understanding. Does that make sense?
It's validates.
And whoever writes the agent should also write the MCP server to let other people talk.
Yes, yes, yes.
Now, I want to make a comment to validate my thoughts because you comment agent to agent is via internet, you know, could be across the firewall, different company talking to each other, agents. So it reminds me about the Internet of Things, right? So in this case, it would be Internet of Agents. That might be the newer like a paradigm coming.
Yeah, it's just that it will they'll share the Internet of Agent with the same internet that we are using, essentially. So
right.
yeah.
But Google just named it A2A.
Yeah.
Agent to agent. That's just how they're branding. They could have branded it Internet Agents as well.
Exactly. So the internet, like a framework, human initially read it, and then the smart devices, and now it become an agent.
Yeah.
Yes, there is. Yes. Yes.
Can you repeat before?
Yes, the gentleman there, he commented that not only agents can communicate each other through internet, but also on the common hardware platform where they are hosted within the same company. Yes.
Do different vector database vendors share the same MCP spec, or does each have their own MCP spec?
So ideally, given the framework is now defined, most of them try to homogenize it because then it becomes easier for like essentially those vector databases and their creators are vendors. So they want like their solution to plug in some client's original solution where a conventional MCP was used, then it becomes easier. So it is in their own betterment if they stick to the conventional standards and not invent something radically of their own unless it is like highly beneficial or better differentiated from the existing one. Yes.
So, I mean, you have like more and more agents coming up, and you have so many tools changing as, and then prompts are getting more complex. And now, if you introduce agents like living somewhere else on the internet, like how do you handle latency? If it's something like, I know if you use deep research in ChatGPT, like that takes time and intensive, and it takes time, and then the agents are working in the background. But if it's something where you're waiting for a query, and the user has asked something and you're waiting for the response, how do you handle latency? So many agents and then overweight, and you just end up waiting, right?
Keep in mind that all agentic multi-cases are not necessarily interactive. Right?
Yes.
So you have reactive applications that are using agents to do things in the background, right? Where that latency may not be.
Yeah, something like research on ChatGPT would be like something the user can't do. Also, other applications like so you just don't use these frameworks and like post it remotely.
So essentially, like my scope of the lecture is assume as an analogy limited to the app store. So for example, if I have say an iOS app, I'm worried about how my requests I can control my side of latency optimization part and not worry about the internet, because it essentially is going to be same for all other companies. So if like 5G internet is with me as well as my competitor, then I'm the least worried about that internet latency, because it's the provider's problem and not like my agent system's problem. So here are some open source multi-agent ADKs. LangChain, Swarm by OpenAI. So you can use either of these. Some of them have like RL capabilities, like they support RL loops, and some of them don't. So if you want to inculcate eventual RL loops in your workflows, then you would ideally like to go with these. Swarm by OpenAI is something which is lightweight for orchestration. Like some of these solutions are good for POC building, and some of them are like good for production ready systems. Now, finally, agent evaluations. Using LLM as judge. So LLM-based judge, we took one example as to how LLM was identifying if the answer was correct revenue versus market cap. But then LLM-based judges for agent demonstrate strong concordance with human evaluators. So given like based on human generated knowledge, the base LLMs are trained. So it is obvious that their judging aligns with human judging, and their biases sometimes align with human biases. So it is given, but they had to go. There are multiple papers validating this, which I have cited. Localized errors mean that the evaluation framework isn't just saying that the agent is failed in a broad sense, but it is able to pinpoint exactly while doing which operation the agent has failed, and in the agent's overall reasoning pipeline. So localization is identifying which component broke down. Was it like goal formulation? Was it like plan incoherency? Or did the action deviate from the plan? So LLM judges can mark specific failure steps. So plan was logically inconsistent versus execution was inefficient, instead of just labeling the entire outcome as wrong. So strong agreement with human annotations. It means that step-by-step error tagging by LLM matched closely to human evaluators, validating the method. So here, the judge part is able to say which specific place the failure happened, and it becomes evident if you log thoroughly in your system as well. So logging is recommended. We'll go through the best practices. So here is one example of localized error detection in the agent. So agent reasoning steps. So first one, the goal was to retrieve the average temperature in the New York City in past 7 days. Then the language model, the agent's brain created the plan that searched the web, extract the data, and generate the line chart. It assigned actions to different agents. So web search for NYC average daily temperature in last 7 days. Action 2 was parse the values from the result, and action 3 was generate the line chart using Python tool. You can see that the chart was generated fine, but then error was localized in action number 2. It extracted forecasted values instead of historic values. So there was almost like a lot of difference in terms of the values achieved as a result. And the judge tags this step as the point failure, matching the human annotation. Now, this is like one specific example. There are examples when logging and error detection in an app where you are getting more than 1,000 inference calls, say, per day or per half day, mapping them like these, it requires for a dashboard and then identifying point of failures and then rectifying them. So now we'll quickly go over the observability techniques, and which will enhance the reliability part. So traceability across agents. So message logs. record all inter-agent communication. We have enterprise level loggers available for that, including prompts, responses, tool calls, and environment updates. Conversation trees store branching paths of the reasoning, like chain of thoughts at the system level for post-hoc debugging. And agent state snapshots capture each agent's knowledge state before and after the critical decision was made. Then the second one is token and action level monitoring, token tracing. This is a very interesting topic. Track token usage per agent to identify runaway reasoning loops or inefficient interactions. Sometimes, multi-agentic simulations, you have assigned limits that the supervisor agent will have like the token cap of say 500 or 1000, and the subordinate agent will have like token cap of say 200. But sometimes, because of maybe vague prompts received or questions received, the action the plans which are made by the agent, they are very vague. So it assigns to a specific agent which is not capable to execute them, and then it assigns that plan back to the supervisor or other agents. So it is like, I don't know, it's in India we have banking system like that the check will flow from one table to another table, and then from the original table. So like no agent will do the work, but they'll keep assigning each other. So sorry about that. I hope I didn't get crucified over this. But then essentially, yes. Yes, going over that. So essentially, you keep track of total number of tokens in the system ongoing. So you keep track of inflow and outflow of total tokens, given that each agent have their upper caps. If it's like a lot of to and fro happening and the work is not getting done, then the overall token count of the system will bloat like anything. So if you are, it can be like 2x, 3x bloating in one specific lane. So as in one specific time period. So you will have an idea about on an average number of requests and the token count. And if it's spiked, then it's an anomaly. And then you need to check which agentic simulation is bloating the tokens essentially. So we have action at so this is one way of identifying, and the second way is subordinate agents. If they get same task assigned like more than thrice, because we have like retrying mechanism as well. Same task assigned more than thrice, back to back, even if they have denied the task, then at the fourth attempt, we should identify the nth number of attempt where the task will be scrapped, and then it will be registered as an error or point of failure, etc., so that this kind of to and fro will not happen. So action attribution, link downstream errors to the agent action that caused them. So data extraction versus versus reasoning errors. So we need to identify where the reasoning errors happened, but then it is entirely up to the foundational model you are using. You don't have much control in this aspect of the system as such. Confidence scores log the model calculated probabilities for the key decisions and actions, and drift and so I hope the token part was clear, the bloating of token and how we prevent that scenario. Drift and anomaly detection. These are like very conventional kind of drifts which happen. So first one is concept drift. Detect when agents outputs diverge from expected patterns over time. So example, financial agent misclassifying expenses after domain shift. So this is like underlying domain knowledge has changed and the drift has incurred. We hardly have any control over it, because it is, unless we are fine-tuning the language model for our domain specifications, we entirely have to rely on the language model providers to rectify this drift part per se. We can, to an extent, mitigate it by using RAGs, but then the system becomes just too complicated. Second one is behavior drift. Monitor if agents deviate from the role specification, planner agent overstepping into executor's domain. So this is like very human behavior, like where the assigned role has become like vague so that you step on the other agent's role. So, or the work not getting done and going into the loops, etc. So statistical alerts, automated checks on response length, distribution shift, or unusual tool call frequencies. So over here, as I mentioned, mostly it's recommended to have token caps, but then we need to identify alerting mechanisms to identify specific bot attacks which give like incorrect or malicious prompts per se. And fairness and bias mitigation, this is like an active, most of the talk that we did today, most of the lanes are part of active research. So when I'm speaking of one result on fairness and bias, it's likely that somewhere one paper is published showing better results. So agent level audits check that outputs across demographic groups remain consistent. So hiring assistant and screening agent, that's like where we used LLM as judge, and then we use LLM as auditor. So this is one part where we eventually need to do data analysis on the on our agentic systems responses as to what questions got answered by what kind of response and how many percentage number of them had like associated bias, and it was specific to one demographic, and that kind of results were not shown in another kind of demographic. So ideally, if your deployment region is same and your method of deployment is same across the board, then these kind of scenarios should not happen. But we cannot completely discount the non-deterministic part of what the system brings. So it is likely that one specific question asked has gotten a specific answer which was correct, but then correct in the measure of fairness and bias, but then the other question, same question or similar question asked, got like different response that we did not like. Now this is
can you
yes.
get two questions on the last two slides? I thank you very much. This is very full and exhaustive, but how real are these? Are you observing this like in 1% of applied field where you're seeing 1% of drift or 1% of behavioral drift? Same thing with token bloating. Is it like a red herring event? Is it a 1% event? Is it a 10% problem? Can you weigh this? So I can speak of like token bloating because that can be experienced by someone who is a developer and who has built like multi-agentic systems. But then concept drift and behavior drift, that can be observed and monitored by my system in a way that so it is almost like I am using the foundational model and getting these kind of drifts, but then correcting them is not entirely in my control. So it's the foundational model vendors who will be able to answer that question more specifically as to how frequently they encounter the concept drifts, because they are the one training the larger model, which I'm only using in my agent as the brain.
One thing you can do as a system is if you reload your system every week or every night, then you can prevent your system from having goal drift.
Oh no, I agree to the solution part. The question is how prevalent is it? Is it something that every 1,000 queries one has to be concerned with? Is it every duration of time? Is it, hey, if you're not pushing to a very concentrated area of questioning?
Maybe I can
answer off.
Yeah, I think concept drift is like prevalent for 40 years. And the idea of loose bands changes every 3 months. So, you know, you have to retrain your system if somebody is asking for new standards. What you showed 3 months ago might not apply to. So it's like some of these are like really, really common.
About how many more slides do you have?
3, yes,
Okay.
will be done 3.
So
It's started in 9, yeah.
Thanks.
Yeah, so this is like putting it all together, observability and responsible AI framework. We did input monitoring in that we validate user queries, detect adversarial prompts, agent interaction and logging, record reasoning steps, tool calls and messages, confidence and drift tracking, token level and decision level monitoring, fairness auditing, continuous bias detection on agent outputs. That's something is in our control. And oversight agents, real-time safety interventions, which is like human interventions to see if your simulation is behaving well, and explainability reports, summaries for end user and eventual compliance. So this is like one last example of a supply chain multi-agent system where we have planner agent who creates the procurement strategy, forecaster agent, optimizer agent who allocates the resources, and in addition to that, we have oversight agent who monitors fairness, which is one way of having LLM as judge only, but then validating that agent validating the system continuously for fairness, and we can feed that agent like specific prompts as to how it should perceive fairness in general. So observability dashboard provides real-time view of agent actions. Here we can include tokens as number of tokens as well, confidence levels and drift alerts. And observability in general ensures that we can see and trace what agents are doing, while responsible AI ensures that they do it ethically, fairly, and safely. And that's our actual goal of building the systems. And you can read through the best practices. I'll share the presentation. You already know them. I covered them. Yeah, these are my citations, questions. Yes.
How much of you? How much of the traceability and other stuff is talked about has been productized and how much remains to be productized? For example, we have things like LangChain that but how much of it?
So token count calculation is something that is very easy to implement. Similarly, fairness, LLM as judge who detects fairness is also easier to implement. The other things are very scenario based. I have never received like those kind of scenarios in that much of bulk to implement others, but they are all in production. These all are, none of these are like hypothetical scenarios. They are built systems.
There are products that are already available.
Yes. Yes.
Where I can use it and where I have. That's my question.
Yeah, maybe we'll have another session for that. Yeah, sure. Thank you so much. Thank you all for coming. Yeah.
Before people go, just for a show of hands, if we have a day-long training class related to this, how many people would be interested in coming? This would be a big thing. Keep your hands up so I can count.